Welcome to NPTEL. I am Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching advanced materials and process. Today, we will try to learn the different classifications of advanced materials, which means structural or functional. As I discussed earlier, that 9 engineering properties are very much important for any applications. So, in the left hand side you can see these are the properties. Materials has been selected based on all these properties like acoustical, chemical, electrical, environmental, magnetic, mechanical, optical, radiological, thermal. Usually among all these 9 properties, these mechanical properties are very much important for any structural application. So, the structural application is somewhat important. However, mechanical properties means strength, toughness, fatigue, fracture and all these. Ductility, malleability, all these properties falls under mechanical properties. However, when a structural material is selected, not only these properties are verified or characterized whether they really show the desired properties or not. However, some other properties are also scientists usually look at, like environmental properties. If we like to make a offshore structure, then material not only should show a good strength and mechanical properties, however, they should show also good properties to combat any kind of corrosion, whether it could be aqueous corrosion or it could be some other kind of high temperature corrosion. Like if we have to design a turbine, then both mechanical properties as well as high temperature properties are important. Whereas, usually all these other properties are considered as a functional properties of materials. So, we usually see these two different categories where structural properties and functional properties, and the materials used for them are called as the structural materials or functional materials. Now, let us see the wide variety of advanced materials which are keep on going developed day by day, and what are those materials, and if we can simplify all these different materials. So, in the left hand side you see I have listed the structural materials like advanced low alloy steels or high strength steels, lightweight alloys. We know the density of aluminum, titanium, magnesium, those are very less, below 6. Also we can make very lightweight structures by some foam or metal foam, where a metal network structures is there which is in combination with some air bubbles, those are called as foam. Also the advanced composites, these composites are being developed in consideration with high strength to weight ratio, also very high stiffness, like if one has to design a aeroplane wing. So, the stiffness should be very high, otherwise the wing will be bended, and therefore, composites or some lightweight alloys with some composite microstructure, laminate structure, all these things are considered. At the same time, these composites are also prepared for good shock absorbance property, etc. Now, the fourth class of materials are particulate materials. Particulate materials means metal with particle shape. Those particle size could be different from micrometer to nanometer in different length scale, and those are usually processed by powder metallurgy technique. And we take the advantage of additive manufacturing technique, where we start from the powder particles and use some energy source, whether it could be laser, and then integrate or make bonding between those particles in order to make a bigger object or desired object or pre-designed object using some software. So, the laser beam runs across a pre-designed shape, and that is called additive manufacturing. There is definitely a large benefit of this additive manufacturing over conventional casting process, because we know the pre-desired shape, we do not need any risering, or like in case of casting almost 40% metals are become useless because of cutting down of the risers and different gating system and so on. Therefore, this additive manufacturing become very much popular these days, where 98% metal could be utilized. Now, the other category of materials usually for higher temperature, here high temperature alloys like silicides based composites or super alloys, which are used at higher temperature. Here higher temperature means we are talking about above 300 degree centigrade and so on, up to let us say something like 1000 to 1200 degree centigrade, and people are keep on developing these alloys. On the other hand, there is also another category of materials, those are called as ultra high temperature materials. Here materials we intentionally use because those are mostly ceramic, because the melting temperature of ceramics are very very high, mostly above 2400 degree centigrade, and those ceramics can sustain very high temperature and can retain the strength, and therefore, there is a large effort is being made these days to develop these ultra high temperature ceramics. Whereas, the second category of these advanced materials are the functional materials. The emerging or very recent development of these materials has occurred, like glassy and amorphous alloys, nanomaterials, biomaterials and devices. In all these three cases, definitely we need some mechanical strength, otherwise we cannot use these material. At the same time, there is also need some other properties which are functional properties. Now, lot of other materials also have emerged these days as a functional materials, like electronic material, like energy materials, means energy storage as well as energy harvesting, either from sunlight or maybe some other sources. There are several optoelectronic materials and devices, smart metals or materials like nickel titanium, where material remember its shape, that is called as smart material, or maybe piezoelectric materials, and all these materials falls under smart materials. At the same time, there are a large effort also getting involved to develop rare earth based functional materials. In several magnetic materials, sensors and so on, there are so many applications of rare earth element and so on, which are very much important. Now, let us start with the structural materials and how we are going to apply and develop the steels from very old concept. On today, if we look at the structural component of a high end car, which are shown in the left hand side here, you see different colors are given in order to show different grade of steel, where a conventional grade of steel are well known, which are also used for any kind of household structure making, like mild steel or low carbon steel. But there are large number of steels are also used for constructing the car. These are the portions which are made out of low carbon or mild steels, but here we use high strength low alloy steels. Here we use bake hardened steel. This is a very special grade of steel where carbon atom are purposely sit down near the dislocation core, and it increases the strength almost 3 to 4 times. If a mild steel has a strength of 200 megapascal, the bake hardenable steel goes up to 700 megapascal. On the other hand, they have a very good quality of malleability. Now, dual phase steel are also often used for constructing. Also, little part of aluminum or press hardened steels. In the right hand side, you see the total percentage of the steel used for any car, where dual phase steels cover around 30%, where more than 20% of the steels are used as a high strength low alloy steel, and bake hardened steel is almost like 17.5%. Only 17% of the steels which are used for constructing a car as a mild steel. So, one can see that how a large amount of advanced structural steels are used these days even for making a car, and the demand is also high to develop these high strength steels. There are many mechanisms, there are many assumptions or simplifications, microstructural basis and so on for development, and there are definitely a certain amount of tempered, matte tempered means martensitic tempered steels are also used around 5%, whereas 5% are used as a aluminum and press hardened steel in this range. So, one can see that even these days for constructing a car, all these advanced steels are used. Now, let us have a look at the area of the opportunity, like the bake hardened steels, as we said, HSLA, dual phase steel and complex phase steels, advanced high strength steels. You can see here, this is a plot of elongation versus the tensile strength. One can see the conventional steel have a strength level of 200, where one can get something like 50%, where interstitial free steels give you very high ductility and very poor strength, whereas HSLA steels are lying here, which has something like 10% and 500 megapascal strength. The MART stands for the martensitic steel, which has very high strength, whereas very poor ductility, means the formability is very poor. So, the current area of research of development of steel is lying here, where we need improved mechanical properties in terms of elongation, means malleability or plasticity or shaping, as well as we need a higher tensile strength, and this is the demand on today. Definitely reduction of the cost and joining of the steels in terms of weldability is also important, whereas one can look at the austenitic based steels or very highly alloyed steels. They have relatively higher ductility or elongation, as well as relatively higher strength than the conventional steels. Also, there is another category of steels which is also at advanced stage, that is called transformation induced plasticity. Here during deformation a austenite phase transform into martensite. Okay. And also there could be some twinning induced plasticity, and these strip gauge steels are also very well known for very high toughness, because they absorb very high energy before failure. Now, let us look at, for the structural materials, the lightweight alloys. In case of lightweight alloys, mostly aluminum based alloys, titanium alloys, magnesium alloys and their foam are quite relevant. In case of making a aeroplane, as an example A380, one can see that how much is the usage of different aluminum based alloys, and you can see all over. So, the fuselage panels, okay, the floor structures, okay, and then the upper wing, lower wing, internal structures, the wing box, fuselage panel, all of them are made out of aluminum alloys or aluminum lithium alloys. There are different grades of aluminum alloys. On the other hand, one can look at a very old model of 747 Boeing, and these days 777 Boeing. Here also the application of aluminum alloys are very high, almost 80% and also let us say something like 70%. Definitely one can look at the use of titanium has increased a little bit, which is also a lightweight alloys and much higher strength than the aluminum, and let us say the usage of steels are also get lowered with the expense of composites and let us say titanium. So, from the earlier work and earlier ideas of using composite has changed, and from 1 to 11%, almost 10% has increased these days. Also, as I said, that the metal foams are very much important to produce lightweight materials, which is basically a composite like microstructure with air bubble in a metallic component. So, I show you two of the example from the Ferrari 360 and 430. Here is one component, that is a aluminum foam, also the Audi one component. These are all foam structures. Mostly it looks like a cellular structures. So, cellular structures means these are the metal part and inside there is air bubble. Okay. And it is made of a solid metal containing large volume fraction of gas filled pores, and these could be open pore or maybe the closed pores. However, the key properties of such metallic foam is ultra lightweight, because 75 to 90% of the volume consists of only void or spaces due to very high porosity and very high compression strength combined with good energy absorption, because whenever we put some thrust, then these foam structures basically here breaks and it absorbs lot of energy, because once it breaks then the crack tip get blunted, because there is air inside and it has to find out a neighboring places where the new crack has to be opened, and therefore, it can absorb a very high amount of energy. Thermal conductivity is also low, yes, because of the discontinuity. Also their relative strength to weight ratio is also high. So, that is why we choose these lightweight alloys for structural purpose, and also metallic foam for any kind of energy absorption purpose or also for construction. Now, let us talk about the composites. And what is the idea of composite these days? Because even for making flight, so much composites are in use. So, here I show the conventional aluminum alloys or steel or titanium, which are shown here with yellow color, and the pure aluminum is also used. So, this is the area where these alloys are used, whereas the rest of the structures are used with carbon sandwich composite or carbon laminate composites, and also with some fiberglasses. So, here these are the component where fiberglass is often used, and here some sandwich composites are used, and these are the laminated composite, even though the outer case is made out of aluminum alloys. So, the total material that is used for making such flight by weight, one can look at where the composite structures inside by in terms of weight is almost reaches up to 50%. So, by comparison, the 777 uses 12% of the composite and 50% of the aluminum. So, here you see that there is lot of development is going on, even though the idea was to use lightweight alloys, but these days the lightweight alloys, advanced alloys are also replaced by advanced composites. Along this direction, one can look at that why these composite structures are often preferred compared to conventional aluminum alloys or titanium alloys or steel, because the carbon fiber has almost a large specific strength, means strength with weight ratio than these titanium or steels or any glass fiber. So, glass fiber used as reinforcement with some other magnesium or aluminum matrix that can also be used. The total global carbon fiber demand in terms of metric tons in 2009, which almost become 3 times in 2019 as expected in aerospace sector. In consumer sector, it will be almost like double. In energy sector, it will be also 5 times, and therefore, the total carbon fiber demand is going to increase, and one can see the total multiplication factor by these 10 years from 2009 to 2019. So, there is definitely a large demand for making composite using some carbon fiber, and also carbon has a very great advantage, because carbon has the highest melting temperature among all the different element in the periodic table. Now, let us discuss about the particulate materials which are used for structural purposes. We know about all these tungsten filament which is used in our home. So, these are very small spring and made out of tungsten. There is often a sagging occur due to long usage, and the filament goes breaks actually. However, they are produced by this powder metallurgy technique, and the same technique from powder particles we make a larger shape. Iron and steel sector, copper and its alloys, tungsten, tungsten carbide means basically cermet and so on, where tungsten carbide plus cobalt matrix are used. Molybdenum and magnesium alloys, and also nickel, tin, aluminum, all these products, many products are made from this particulate shape. And here one can look at how intricate the automobile parts can be made out of this, like a gear and lot of component, also for trimmer blade where very intricate structures can be made. So, the additive manufacturing is a manufacturing technique to start from these particles and to make materials for use for electrical contact materials, powder metallurgy fibers, heavy duty friction materials, self lubricating porous bearings, carbide and alumina diamond cutting tools, structural parts and the surmate of high tech application. So, we have a large use of these powder particles to start with and to make more intricate shape with a very fine and intricate structures. The particulate materials by using this additive manufacturing technique for making products or services are shown here in terms of the market value and the market growth from 1993 to 2013, last 20 years. And one can see a exponential growth of the market of these particulate materials for structural purpose in terms of strength. The very similar kind of scenario one can look at the value in terms of US $1,000,000 with the year, the history of the material sales as per the worldwide using these additive manufacturing technique. And this is the metallic materials which are still very less compared to other kind of materials, means ceramic or polymer. Okay. So, the total market value in terms of US million almost reaches to 3000 million in the year 2013, and these are the recent data. One can have a look at the scenario of current development. Now, there are also alloys which are developed for a quite long time from 1990s for used in the gas turbine for the development of space vehicle and also for the aircraft. Here the nickel based superalloys are quite important. In the left hand side we see a gas turbine engine where the gases enter through the compressor which goes through a combustion chamber, and this is the turbine here and goes out of the exhaust nozzle. So, like as an example GE or Jet Propulsion General Electric engine, Trent 800 for GE 90 Boeing 777, those are used for temperature greater than 800 degrees centigrade, or let us say for electricity generation 250 megawatt of those kind of gas turbine engine which can cater service to a city of millions of people. And the production technique has changed time to time from wrought alloys to conventional alloys to cast alloys to let us say the single crystal cast alloys. And here these are the engine model trend from GE, and one can look at that even though the material are developed by most sophisticated technique, but there is a large gap between the takeoff temperature. So, here turbine entry temperature is the temperature which is very crucial to get a much better heat extraction from a Carnot cycle. The previously those turbine blades were undercooled, uncooled, and here these are the cooled turbine blade, and in the recent days the thermal barrier coatings are often used. And one can definitely look at the benefit of such. I show you here the microstructure of such a superalloy, nickel based superalloy, where gamma nickel is this phase and the white colored phase are the nickel 3 aluminum precipitate, which is a ordered intermetallic, and at very high temperature it assists on dislocation passing when dislocation going to pass, it has to cut through, and this is a deformed microstructure of such a superalloy. So, you can see we can increase the strength of this gamma nickel matrix by these precipitates, and these precipitates are ordered structure of L1 2 structure of nickel 3 aluminum, and this is the strategy of developing superalloys. So, today we have learned the different categories of structural materials, and functional materials will be discussed in the next classes, and we tried to understand how these advanced materials are classified, and even today there is a large demand on developing advanced high strength steels. So, one has to look at the lightweight alloys, the advanced high strength alloys, the foam structures, making some intricate structures from starting from metal powder, where utilization is very high, yield is very high. It does not go like a casting technology, where metal utilization is less, and so on. Thank you.